So earlier we have seen that it is possible to combine the mixer and a driver amplifier to result in a power mixer. And the power mixer can solve the problems where we may have to worry about this interface between the mixer and the driver amplifier. We will see that in the modern communication device, it needs to support multiple standards. For example, for wireless connectivity, we may need Wi-Fi, Bluetooth, and for cellular communication, again, we may need to support 4G, 5G. So a system needs to be compatible with multiple wireless standards which are present in the connectivity as well as in the cellular communication. And if we require multiple radio modules to support each of these standards, then we can see that the overall cost of such a system is going to increase. In addition to that, the overall size is going to be large. So there is a motivation for trying to design a transmitter which can support multiple radios without actually requiring separate transmitters. And we have already seen that to support a specific standard, we need to design a DAC with a sampling rate followed by this anti-imaging filter. This anti-imaging filter requires very precise passive elements for the high amount of image rejection, followed by a mixer which is driven by again the arrow which is centered around the required frequency band. Now, if we can try to combine this generation of the RF signal from the digital, then it is possible to design a transmitter which can generate the RF signals for different kind of standard without too much worrying about the bulky analog blocks which are present in a standard transmitter chain. So this is the motivation behind designing a RF-DAC. So a radio frequency digital to analog converter can take a digital input and directly generate an RF output. And by keeping all those blocks mostly digital, it is possible to design a transmitter which can support multiple wireless standards. So we are going to look at the design of a radio frequency digital to analog converter, which converts digital input to RF output. The idea is we can combine DAC followed by the filter and the mixer into one block. And to understand what are the possibilities of merging these blocks, let us try to see the circuit of the active mixer, which was already discussed earlier for the up conversion. So the active mixer had these transconductors which were converting the baseband differential voltage input into the currents, and finally this current was steered with the help of switching quad. And the output we could generate by using a tuned load, and this tuned load will convert this current into voltage. So here, if you remember, this was the V2I converter, transconductor, whereas these 4 transistors were forming the switching quad. This is active mixer. If we look at the DAC, then this DAC can be designed using a popular circuit topology which has currents which is being steered to the load depending on the digital code. So that current steering DAC can generate an output in the current domain directly, and later on which is converted into the voltage with the help of some load. So this DAC can be designed using a current steering topology which has these current sources and this current is steered towards the load depending on the digital code. T0, this is, let's say, T0 bar, some Dn, Tn bar. So by using this kind of current steering topology, you can design DACs where the output is in the form of current, which can be converted into voltage with the help of a load. This current steering DAC is also a very popular topology. So one point to note here is that in the case of active mixer, also we generate this baseband current, which are finally up converted with the help of switching quad. And in the case of current steering DAC, it can also directly generate this baseband current. So it should be possible to take this current steering DAC and completely replace with the V2I converter in the active mixer. And if we can do that, then we can see that in a way we are able to merge the DAC with the mixer itself. So this is a very simple way of merging the DAC with the up converting mixer. If we replace the V2I converter with a current steering DAC, in this way, the DAC and the mixer can be merged. So here we note that the V2I converter in active mixer be replaced with current steering DAC. So here we can see that this current steering DAC in place of the V2I converter in an active mixer effectively is doing the job of the DAC in the standard transmitter chain as well as the V2I converter in the active mixer. We can see that there is no anti-imaging filter as such in this architecture. So let us try to look at how the spectrum is going to look for the baseband current and the RF output as compared to the spectrum of the signal in the digital domain. So let's say this is Fs, 3Fs, here is the Fs by 2. So the digital data is going to occupy some spectrum, let's say, which is till Fs by 2. So here we are showing the single-sided spectrum. So this is D in. Once the digital data has been passed through the current steering DAC, where the current steering DAC has a zero order hold kind of output. So the output of the current steering DAC is going to see sync kind of filtering. So if we draw the complete spectrum of the baseband current, it is going to have almost same spectrum as the D in band. But in addition to that, it will also be having images, and these images are going to see the sync filtering. Images may look like this. So the plot in the green shows the spectrum of baseband current. And the baseband current is the zero volt output of current steering DAC. So we can already see that all these images are going to be present. So these are DAC images. And now if we are going to look at the output spectrum and the RF, let's say this is the center frequency of the RF output. Fs RF minus Fs. Then it is going to like the main signal in the Nyquist zone, which is this one, to up convert to the FRF frequency. In addition to that, these images will also appear. So we will have like this. Now we can see that at the RF output, so here is your VRF is equal to VRF plus minus VRF minus. So at the RF output, we are going to have all these images, which will also get amplified by the succeeding stages and going to be transmitted. So this can be a big issue for any receiver operating in the neighboring channels. So already there is spectral mask in place, and this kind of output spectrum is never going to pass the spectral mask. So we need to suppress these images so as to pass the spectral mask and transmit the upconverted signal. So the simplest solution we can think of is putting a band pass filter in the RF domain itself so as to reject these images. But we can see that the design of such a band pass filter in the RF domain can be really challenging if these sampling frequencies are very small compared to the center frequency. Band pass filter at RF can be used to reject DAC images. But this filter design will require very high order bulky filter. In addition to that, every time this center frequency is going to change, this filter also needs to be tunable. So overall, the transmitter can become too complex. High order tunable BPF. So what is the other solution? We've already seen in the case of anti-imaging filter design that if we can push this sampling frequency to a higher value, then automatically these images will be appearing at a higher offset. So as a result of which, we can afford to have a more shallower roll-off for the bandpass filter at the RF and still reject the DAC images. We use over sampling to push DAC images away from interfrequency to simplify BPF design. Okay, so over sampling. But one issue is now again we need to have those filters at the RF, and even though the order has been reduced, but still we need to make those tunable bandpass RF filters. So it is not a complete digital solution. It requires still some tunable analog components, which dilutes the overall motivation of using a RF-DAC. So the idea was we can just give a digital input and generate an RF output. And in between, we were able to get rid of the anti-imaging filter at the baseband. But now we are just pushing that filter into the RF domain. So which is not exactly simplifying the overall chain. Not desirable as this will still require tunable BPF at RF. So what else can be done? So here we can see that these DAC images see only sync kind of filtering because we have a zero order hold pulse shaping at the output of the current steering DAC. What if we can improve the interpolation at the DAC output so as to get a better filtering? So to explain this, let us draw the time domain waveform at the output of the DAC. So we can see that at the DAC output, we'll be having these kinds of zero order hold waveform. Where this is the sampling period Ts, then 2Ts. And we can see that every sample, we are going to just hold the output, which is giving us the sync filtering. We know that instead of doing a zero order hold, if we do first order hold or linear interpolation, then we will be getting a waveform like this, where the signal value in between the sampling period has been linearly interpolated. So this kind of DAC gives a better filtering than the simple zero order hold, and we know that this is going to add a sync square kind of filtering for the DAC images. So this is the first approach which we can try to attenuate the DAC images. So the linear interpolation will look like this. This is zero order hold output. This is linear interpolation output. Corresponding frequency spectrum, if we have to take a look. So for the case of linear interpolation, we are going to get a sync square kind of envelope. So this is zero order hold. This is sync envelope. So this sync envelope will have the frequency response as sine pi f by fs divided by pi f by fs. Whereas for the linear interpolation, we will find that the filtering is having sync square envelope. So the envelope is going to look lower than the sync. This is sync square envelope. Which is square of the sync envelope. Sine square pi f by fs divided by pi f by fs whole square. As a result of this, if you look at the spectrum after the linear interpolation, it is going to have almost the same spectrum as the sync in the Nyquist zone. But after that, it is going to show much higher attenuation. IBB dash interpolated output of DAC can have much lower DAC image strength. Many times this alone may not be sufficient. So it is possible to combine oversampling along with the linear interpolation so as to keep the DAC images below the spectral mask. But one practical problem is how to implement this linear interpolation. Now let us try to see how we can realize an improved interpolation DAC. Let's say the initial samples of the digital input were like this. And if the DAC is generating a zero order hold output, then that would have looked like whereas if we are looking for a linear interpolation, then this linear interpolated DAC output should look like this. Also called as first order hold linear interpolation. To be able to do a linear interpolation from the digital samples requires very complex analog filters. So what we can do is we can do an approximation to the linear interpolation, where if we want to interpolate between the two digital samples, for example like this, so ideally we may want to do a straight line interpolation in between these 2 points. But to simplify the hardware, what we can do is we can try to move to the next sample in a staircase approximation manner. So the idea is, if we have enough number of steps like this, then in the limit it is going to approach a linear interpolated output, and at the same time it is possible to design a hardware which can give this kind of staircase output in a much simpler manner as compared to a pure linear interpolated output. So what we can do is, if we are starting from this sample, instead of taking the complete jump after the sampling period Ts, we can split the jump into small steps, and we can start the output to change after much smaller duration as compared to the sampling period. So here, for example, we are taking a jump at Ts by 3, and then again we can hold the output, and then next 2 Ts by 3 we can again change the output, and finally at Ts we can reach to the final output. Similarly, let's say when we are going from the sample at TS to sample at 2TS, we can make the first change at TS by 3 after the TS, like this. And you can see already that this jump which we are making is also scaled as compared to the jump which is present in the case of the zero order hold output. If we are doing the interpolation in 3 steps, you can see that this jump is also reduced by 1/3 of the total jump which we would have got in the case of zero order hold. And like this, finally we are going to reach the required output. So this is also called as L-fold interpolation. Here we can see that the number of steps which we are taking is 3. So this is a 3-fold interpolation. Already it can be observed that for high value of L, this approximates to linear interpolation. And the most important point about this L-fold interpolation is that its hardware realization can be much simpler as compared to a linear interpolation. Compared to linear interpolation. So we can briefly take a look at how this 3-fold interpolation can be realized with a simple hardware. So looking at this staircase output of the L-fold interpolation, we can already see that if we want to go from one sample to another sample, what we can do is first we can reduce the step size to 1 by Lth value of the actual step size. And at the same time, we can see that after the TS by L delay, we can add the 1 by L scaled value of the jump with itself so as to change the output in this staircase manner. So let's take an example of 3-fold interpolation. So we can see that we can start with a zero order hold value of the analog output, but which has been scaled to 1/3. This is zero order hold kind of output. So what we can do is we can add a delay. In our case, TS by 3. And after this delay, we can take this output Then what we can do, we can add one more TS/3 delay, and now we can add this output as well, so that we get the second jump. And finally we can add this one more TS/3 delay. So that we get this IBV, which is a threefold interpolated output. So if we have access to these delays which are fraction of the sampling period, then it is possible to take the same digital input which has been held for the entire TS period, and just by doing this fractional delay and the summation of their outputs, we can obtain this staircase kind of output. We can also take a look at the impulse response of this threefold interpolation to understand what kind of filtering action such an interpolation can add at the output of the DAC. So here we can see that for the impulse, this held output is first going to be delayed by TS/3 and will appear at the output. So we are going to get a jump here, then second jump, and finally after TS we are going to get the third jump, and after TS time the held output at the input of this interpolation filter is going to go down. So we'll see the downward staircase like this. Now if you plot the impulse response of a linear interpolation filter, that is going to look like a straight line, and then again coming down a straight line. So this is your linear interpolation. Threefold interpolation. So the Fourier transform of this first order whole linear interpolation output is a sinc square. And here we can see that if we have an L-fold interpolation where we approximate this linear interpolation with a large number of steps, then its Fourier transform is also going to approximate sink square kind of envelope. Now let us try to see specifically in the case of the current steering DAC how we can implement this kind of L-fold interpolation. First thing what we can do is we can split the current steering DAC into smaller units. Let's say we are going to do L-fold interpolation. So we will split the DAC into 1/L of its size. The idea is that in the current domain, we can always just add the outputs by just connecting the output nodes together. So by splitting the DACs into 1/L of its strength and connecting their outputs, we can achieve this summation in the current domain. Okay. Now each of these DACs will take a digital input as well as a sampling clock. So the digital input we can generate out of a register which will hold the value for the entire sampling period. And for the clock, we can generate a clock signal which is delayed by Ts by L and fed to each of the subsequent DAC units. Ts by L. Yes. So with this kind of simple structure, we can have a current steering DAC which is still taking a digital input, but now having various subunits which are clocked with different clocks, which are all again having the same sampling frequency as the digital input, just that they are all shifted by Ts by L. This is L-fold interpolation and steering DAC. Now such a DAC can be directly connected in the active mixer circuit which we have shown earlier. So we're taking advantage of this improved interpolation and also increasing the oversampling. It is possible to keep the output spectrum of an RF-DAC to be below the spectral mask. So here we can do oversampling as well as we can do better interpolation than just zero order hold. And one case we have already seen with the help of L-fold interpolation. So together, it is possible to keep the DAC images below the spectral mask. Together, RF-DAC output. Happened without any anti-imaging filter. So this kind of circuit, you can already see that is going to be highly reconfigurable. This circuit is also called as digital RF amplitude modulator. RF amplitude modulator. So another name for RF-DAC. This architecture has several advantages in terms of saving area, being very low cost, highly reconfigurable. But still we can see that since the entire digital to analog generation has been concentrated in this current steering DAC, so the non-idealities of this DAC will also be affecting the overall performance. For example, when there is a swing at the output, that will also be appearing at the output of the DAC, and this may also result in some non-linearity in the baseband current and finally at the output. So from here we can actually see that since this current steering DAC already contains the switches and current sources, so is it possible to merge those current sources, switches along with the LO such that overall we can get a more optimized design where we don't have any such pure analog nodes present in the circuit which can undergo this kind of non-linearity.